Welcome to the vodcast on length contraction from Einstein's theory of special relativity. Our goal, as you can see, is to understand what length contraction is in special relativity and to be able to relate measurements of length in one reference frame to the measurements of that length in another reference frame. So to begin to understand this idea, we're going to go back to a thought experiment that I used in my third vodcast on special relativity, which was to do with the relativity of simultaneity, which is at the heart of everything in the theory of special relativity. Everything comes back to the idea of two events that might be simultaneous in one person's reference frame not being simultaneous in another. So we're going to go back to that idea. So we had this thought experiment that we were looking at in that vodcast, where a train with a person on it was passing a platform that also had a person on it. So the train had a speed relative to the person on the platform, or a velocity to the right. And these two people in their experiment agreed that when the front of the train passed the front of the platform, a flash of light went off, and when the back of the train passed the back of the platform, a different coloured flash of light, so a blue light would flash. And what we got from that experiment, and I won't go through how we got there in this, but what we got from that experiment was that the person on the train would say that this event occurred before this event. Or I should say, if this person measures these two events to occur at the same time, then this person on the train will say that the red event will happen before the blue event. And if you want a reminder of that or an explanation of that, go back to the third vodcast on the relativity of simultaneity. So using that idea, we were able to talk about how time dilates. So two people measure different times to have elapsed between two events occurring. The flip side of that, and you're starting to see now that time and space are related, this means that length or distance is also affected in this idea. Now let's look at why. If this person says that these two events occurred at the same time, then the only way that that can make sense is if this person says that the length of the platform is the same as the length of the train. So if these lengths were not the same, then there's no way that these two events could occur at the same time. So let's say that this person measures the length of the platform to be L0 or L0, and again I'll go into that terminology shortly. So he would say that that's L0, and he would say that the train is must be the same length because these two events occurred at the same time. But now think about it from this person's perspective. If we agree that this person measures the front of the train, or measures this blue flash to have occurred, this red flash to have occurred before this blue flash, then what that's saying is this person measures the front of the train to pass the front of the platform before the back of the train passes the back of the platform. Now that's not possible if these two objects are measured to have the same length. So just to demonstrate that, so say these are our two objects. So here's the train, here's the platform. Given that they are the same length, as the train passes, then here's the event where the front of the train passes this end of the platform, and at precisely the same time, the back of the train passes this end of the platform, because they are the same length, which is handy because both the train and the platform are manufactured by the same company, BIC. Thank you very much, BIC. On the other hand, if we have a shorter platform like this, then as the train passes, the person on the train measures right here, the front of the train to pass this end of the platform, and then sometime after they measure the back of the train to pass the back or the left end of the platform. So the only way that this person can be able to explain the idea that these two events are not simultaneous is if the length of the platform is shorter than the length of the train, which means that this person is going to measure the platform to be squashed. effectively, which is where this idea of length contraction comes from. So to just introduce the definition, L0, which I said here, is the proper length. And what that means is it's the length measured in the rest frame of the object. So if you just look at this, this person on the platform who's measuring the width of the platform is able to do that with a ruler in his reference frame, and he doesn't need to worry about anything moving because the platform is not moving relative to the ruler or the tape measure or whatever he has. So we call that measurement a proper length. But again, I want to stress the idea that this word is a little bit misleading. It doesn't mean that other lengths are incorrect in any way. It just distinguishes a measurement in a reference frame that's not moving relative to the thing you're measuring, compared with any other length which is made when that reference frame is moving relative to the thing that you're measuring. So any other measurements that we make, any measurements we make of the same object but from a reference frame which is moving relative to that object. So what I'm talking about specifically is if this person is moving relative to the platform, any measurement this person makes of the platform will always be less than the proper length, which again is why we use the term contraction. So we always have time dilation, as I spoke about in the previous vodcast, and we have length contraction. We don't get length increasing, we get length contraction. Something that's really important to point out here as well is that the contracting always occurs in a direction parallel to the motion. So what I'm saying there is that as this person passes the platform, they will measure a shorter length of the platform in this direction. It will not affect any measurement they make of the platform in this direction, for example. That will always be the same. So just to show that, I guess even more specifically, if we had in a proper length of some square object, excuse my bad drawing, so say in the frame of this square object that's not moving, these are the measurements you make. Someone who's moving past that object, so someone who's moving in that direction past that object, is going to measure the object to look like this. So this dimension of the object has been squashed, but it hasn't affected this vertical dimension. So it's really important to be clear on that. There are certain to be exam questions that come up about that idea. So with those definitions of what proper length is, and to understand that the measurements are always contracted, then we can relate them mathematically according to this. Now I'm not going to go into the derivation of this. It's quite similar to the one for time dilation, which I did do in the previous vodcast. I'm not going to do it here, but I'm happy to go through it with you if you like, or you can easily find it on the internet. So any other length is going to be equal to the proper length divided by this Lorentz factor, which we introduced in the previous lesson. So this gamma represents the Lorentz factor, and it's the exact same gamma as in that previous episode. So it's made up of 1 divided by the square root of 1 minus v divided by c squared, where v is the relative speed between the two reference frames. So a question that you might legitimately have from all this is it real? Is it real that things are getting smaller? Is it real that length is contracting? And it's a really great question to ask, and this is where I think this element of physics is so fascinating, because it starts to merge to an extent with sort of philosophical ideas, because the question really then becomes what do you mean by real? So if reality is just based on observations and measurements, which it really is, and if those measurements are always consistent and no error can be determined in those measurements, then what you're observing and what you're measuring is real. There's no other reality from that. So in that sense, the object really is shrinking. The platform really is shrinking. Or maybe another way that you might put it is the object is really measured to be shorter. It's really measured to have shrunk. So using the word measurement is a good way of describing this. And the same thing happens with time dilation. So we would say, as with the example we gave in the previous episode, that the time has really measured to have taken longer. Time really has been measured to have dilated. And so in that sense, the clocks are running slower. Time has slowed down for these two people because your measurement really is your best indication of reality. Another interesting question, which I'm not... no, I will answer it. But a good question, I think, to be able to ask is, how does this person explain the fact that this person has measured a greater length? And so again, it comes back to the idea of simultaneity being relative. So this person will measure the platform to be shorter, but if we were to say to this person, well, hold on, the person on the platform said it's bigger than what you measured, what's the deal with that? This person will completely correctly say, well, this person did not take the measurements at simultaneous times. If we want to measure how big an object is, we have to measure that object, the two ends of that object, at simultaneous times. So if something's moving past, it doesn't make sense to measure the front of that object at this point in time and say, oh, look, that's at 10 centimeters, and then measure the back of the object at some other point in time and go, oh, look, it's at 9 centimeters. Therefore, our object's only 1 centimeter apart. It only works if we take the measurements simultaneously. But again, that idea of simultaneity is relative. So this person does not agree that these two events were simultaneous. So they'll say, well, person C is an idiot because they didn't take these two measurements simultaneously. So in that sense, we're able to explain the discrepancy. A similar thing is the case with the time dilation that we were looking at in the previous podcast. So I'll just bring that back here. So just to remind you what happened here, someone on a platform was watching this light clock. According to the person in the train, the light is just bouncing up and down, and they're measuring time in that way. The person on the platform sees that clock to go up and down, but also to the right. Because it's travelling a greater distance, but at the same speed, they say that more time has passed. And so they will measure on their clocks, which are synchronized, they will measure a greater amount of time to have passed. But that's entirely dependent on this person synchronizing their clocks, which means they're ticking past at the same time. So this clock says 12 p.m. exactly when this clock says 12 p.m. And this clock says 1 p.m. exactly when this clock says 1 p.m. In other words, each tick of the clock is occurring simultaneously. So then when we come back to this, well, the person on the train will say, but these two clocks aren't simultaneous. So of course they're going to measure a greater time has passed because this clock's running too fast. They're not occurring simultaneously. So this idea of simultaneity being relative is at the heart of time dilation and length contraction, which is why I wanted to spend quite a lot of time on it, even though in the study design, you will not be tested on the relativity of simultaneity itself. But it's a really important idea to understand to be able to have any insight into how length contraction or time dilation actually occur. One final question or thought that I might leave you with is the idea that if this person says that the platform is shorter because this person is moving relative to this, well, what if we were to ask the question about how wide is the train, or how long is the train? So if this person's saying that the platform is shorter, so they're measuring a shorter distance, well then if we kind of flip it and say, okay, now we want to measure the length of the train, so person A on the train will measure the length of the train, and person C on the platform will measure the length of the train. Who's being dilated here? How are these measurements going to compare? That's something for you to think about and perhaps find out more later. Again, if you've enjoyed this podcast, feel free to contribute. Thank you.